You started at one end and you exhaustively searched everything. And that would end up being what we call that order n, but we're just going to call it linear because that's what it is, linear search, that it makes about n, or on average, n divided by 2 comparisons in order to find what it's looking for. Binary search requires that the array be sorted. And if it has that structure, if it has that guarantee, it can exploit that structure by looking at the middle element and saying, yeah, this is the thing I'm looking for, or the thing that I'm looking for, if it exists in this half or in this half of the array, effectively cutting out one of the other halves. If you continue to do this in a recursive manner, you're cutting it in half, you're going from, say, 8 down to 4, down to 2, down to 1. And it only requires a logarithmic number of comparisons to actually do that. So the other component of searching and sorting is, well, fine, we really want things to be sorted because we want to exploit binary search and we want to do fast searching. But how do we actually get to that point? How do we actually make sure that everything is sorted? So there are a huge variety of sorting algorithms, right, with different algorithmic strategies and different performances, right? Strategies and different performances. There are plenty of websites about this. You can go ahead and check out, sortingalgorithms.com or something for some visualizations. You can check out, even YouTube has like dancers that dance and simulate the algorithms to show how it works and stuff like that. So there are lots of ways of looking at this stuff. But we're going to be looking at it from an algorithmic perspective. We're only going to look at a small sample. There are dozens of these algorithms, each with their different performances. We're going to look at 2. We're going to look at one that's bad, efficiency-wise. Then we're going to look at one that's fast, efficiency-wise. But then we're going to reserve most of our time, most of our focus for, no, we're not going to write that stuff. What we're going to do is we're going to use a standard library and learn how to use a standard library so that it sorts for us and we don't have to worry about that stuff. But we do need to understand from the algorithmic perspective that, that some algorithms are fast, some algorithms are slow. All right? And now that we are 5 minutes in, again, if you are here for the Geo Bowl, it is in Teachers College 105. All right? So the first algorithm that we're going to look at today is selection sort. Selection sort is a terrible algorithm. It's going to end up making a quadratic number of comparisons. So it's not, we've got binary search, which is logarithmic. We've got linear search, which is linear. You can have other algorithms that are even less performant. You can go up in the polynomials and call it n squared, n cubed, et cetera, and then exponential algorithms way up there that are completely infeasible, even by today's computers, even by computers 1,000 years from now. I can almost guarantee that, all right? Unless there's some fundamental breakthrough in quantum computing or something like that. So we're going to look at selection sort, and the basic idea is, how would you sort as a human? You look at a list. In fact, let's look at a list now. Let's go ahead and move over here to the .cam, all right? And focus. I like that there's a focus button. All right? Okay. Focus again. There we go. All right. That's good. You can see it. It's good enough. All right. So how would you go about sorting this as a human? I want to sort it in ascending order. So what should I write first? 1. How did you know to do that? You went through, you looked at it really quick and you saw that that was the minimum value, right? All right, well, now that 1 is sorted, that's out of the way. What's next? Sorry, 2, right? All right, you went through and you found that 2 was the next largest, and you keep on doing this, right? Okay, well, 3, all right, and then the remaining one, 5, 7, all right, 5, and then 7, 8, and 9, right? So what were you doing each time? You were choosing the minimum element, and then you were placing that at the front of the list. You were selecting the minimum element and placing that at the front of the list. So algorithmically, what you're going to be doing is you're going to be going through all these numbers, finding the minimum, which you all know how to do because you've done it before. And once you've found the minimum, you're going to end up swapping it with the first element, right? Instead of drawing it horizontally like this. Right? You can if you're going to do a deep copy kind of sorting where you've got the original array and this array, well, you can go ahead and copy that over and then return that copy or something like that. But we're going to sort what's called in-place sorting. In other words, we're going to modify that array so that it appears sorted after it's done. All right? So think about this more generally now. All right? So suppose that we're in the middle of the algorithm, that we've sorted like 5 of these things already. What we're going to do is we're going to assume that the first I elements are sorted. So element A1 through A sub I, right? Or I minus 1. We're going to think about the ith iteration. Is it better? Oh, that's better now. Okay. So we're going to consider that the elements A sub I to A sub I minus 1, these are going to be sorted for us, suppose. Right? Now we've got the remaining elements. We've got elements A sub I through ... A sub n, or adjust everything downward if you're going to use 0 indexing. When we actually code this up, we will. Okay? These are unsorted. So at the ith iteration, describe what's going to happen here. For elements A sub I through A sub n, find the minimum. Right? I'm just using plain old English here. In fact, we're going to start developing pseudocode here. Pseudocode is fake code. It's not C code. It's not Java code. It's not Python. It is more generic than that. It looks like code in that you'll have block descriptions of things. But I'm making liberal use of English here. Maybe you can make use of mathematical notation and other things like that so that you don't have to be specific. I'm not ending my lines with semicolons or anything like that. I don't have opening and closing curly brackets. I don't have const int star. That's not in every language. In fact, C is one of the few languages that has pointers. So I'm not making it specific to any particular language. If I write it out in a more abstract pseudocode manner, then that means that I'm giving you the idea of the algorithm. That idea you can then transcribe to C. You can take that idea and transcribe it to Java. You can transcribe it to whatever programming language you want. Now the problem with pseudocode is, are there any rules? Can I teach you rules to pseudocode? What if I had like a list of all the rules of pseudocode? What would that be then? That would be code, right? That's exactly what code is. Code is a programming language is nothing more than a codification of specific grammars and rules that you can program in, right? Well, pseudocode, it's not any particular language, so I don't have any rules that I can give you. Otherwise, it wouldn't be pseudocode. It would be Python, or it would be Java, or whatever you want to call that, this new programming language, all right? So these are unsorted. Find the minimum element. Once I've found the minimum element, what should I do with it? So I found the minimum element. Say it's this guy right here, m. Right? In fact, I'll even call it m. Right? Help me out. What should I do with it? Where does it belong? Does it belong anywhere over here? No. Why? Because I've already sorted those things. I chose the minimum and I put it at A1. I chose the minimum among the remaining ones and I put it at A2. I chose the minimum among the remaining things and put it at A3 ... I did that for the first I minus 1 elements. Now I need to do this for the remaining elements. So if I find the minimum among all this stuff, where should I put it? At the very beginning. So I will swap A sub I and m. That's the idea with one iteration of this algorithm. Right? Now, zoom out a little bit more. What do I need to, this is one iteration. What should how should I surround that? How many iterations do I need to do? So around that, how many iterations? For I running from, well, in this case, I index it at 1, so I'll start at 1, ... How far do I need to run? Good, n minus 1. Why did you stop short? Why didn't you go all the way to n? because that's already where it needs to be, right? By definition, an array of size 1 is sorted, right? There's one person. How do you align them so that the tallest is first? You just put that one person there, right? So you don't have to go all the way to the end. You only have to go up to n minus 1. Because if you've sorted the first n minus 1 of them, then the last one is already where it needs to be. Okay? Now, with that idea, let's actually go ahead and write this out as pseudocode. Now, again, there are no rules to pseudocode, but the only guideline that I can give you is to make it readable. So my input, first of all, I'm going to label clearly my input and my output. In real code, this is like your parameters to a function. This is like your return type. But not all programming languages work like every programming language has functions, so they kind of all have that similar feel. But this is pseudocode. I'm just going to use these as headers here. My input is going to be a collection. Why didn't I say array? An array of integers, if I want to sort an array of integers. That's way too specific, right? C uses arrays, but there are programming languages that don't have arrays. For example, Python doesn't technically have arrays. PHP is another one. PHP does not have arrays. You can use them as arrays, but they're called associative arrays, which are nothing more than neutered maps, which is another data structure. But not all programming languages have arrays. Some programming languages have things that are different, like lists or sets or stacks or queues or whatever other data structure you want. I'm going to go ahead and make that generic by calling it simply a collection. I don't want to make this C specific. Right? A collection of what? Integers, doubles, characters, strings, student structures. No, those are all way too specific. I don't care what I'm sorting. Right? I just want to describe the process for how to go about doing it. So a collection of elements. And I'll give it a name, A. And I will give each thing a name, A1, A2, ... A sub n. So I've already communicated several pieces of information here. I've communicated that I'm using one indexing, because this is more math than it is CS. And I've told you the size of the collection. You don't have to do, in C, you'd have to do your own bookkeeping and pass in n as a parameter. I'm kind of implicitly doing that here. In Java, you would use a different technique, a .length property on an array, or a size method on a list, or something like that. I'm keeping it general, okay? Now, my output is going to be A sorted, all right? That's going to be my output. Let's see if we can, what if we zoomed? There we go. I'm writing kind of small. All right, but it's readable over there. I'll use a larger Sharpie here. So the collection A sorted. Now, help me out by codifying this. Now, with pseudocode, it's perfectly fine to go ahead and use structures that you would, like control structures like for loops, for each loops, etc. What I'll do is I'll go ahead and start with a for loop. For I running from 1 up to n minus 1. I'm not using the C-style syntax of the idiomatic for loop of for int I equals 0, I is less than n, I++ with semicolons everywhere, parentheses, and opening and closing curly brackets. Not all programming languages do that. Some programming languages use white space to denote block control structures, like Python. Some other programming languages use other things, right? So for I running from 1 up to n, what do I need to do? I need to find the minimum element. So how do you find a minimum element among elements I through n? How would you go about doing that? Maybe write a function and do it for you? Well, that's good code reuse, but this is pseudocode. So, help me out. Yeah. So you're going to do that multiple times, right? So you need another for loop. For j, because I've already used I, running from, say, I up to n, right? In this case, we will want to run I all the way to n because this is the ith iteration. I need to find the minimum. So if the jth element, a sub j, is less than the thing that we've found so far, right, that's minimum, then we need to update it. Well, that means that we need to keep track of the minimum. That's why I left some space here. So what I'm going to do is I'm going to have a min index. And I'll initialize it to I. That would actually allow me to change my for loop and go to I plus 1 because I don't have to compare a sub I to itself to see if it's minimum, right? But I'll keep track of this minimum index. Now, normally, you would write this as min index is equal to I, if that were code. This is pseudocode. So what I'm going to do is I'm actually going to bend over backwards here to force it to make it look like not a programming language, not any particular programming language. So I'm not going to use equals as an assignment operator. I kind of did over here and over here, but so be it. Because some programming languages don't have the equal sign as the assignment operator. Maple, for example. I think Haskell or maybe some R. If you ever programmed the statistical programming language R, I think it uses a left arrow. That is a less than sign and then a hyphen to get this. So it looks kind of like this, basically. All right? So min index is going to be here. Now I can make it my comparison. If if a sub j is less than a sub min index, then I've found something less. So I will update my min index to be j. Right. Here's another part of pseudocode that I'm going to force it to make it look like pseudocode. There is no IDE or plain text editor that would allow you to do anything like this. What I'm doing is I'm aligning this over here. Now you might see in some of your text editors, especially Atom.io, that if you have control blocks and you indent properly, you can actually collapse them, right, with a plus and minus, and you kind of get this kind of behavior on those things, but it's not something you can type out. So that's why I chose to do it this way. Of course, it's most programming languages, C-style syntax, you have an opening curly bracket and a closing curly bracket. Python actually uses indentation for this kind of stuff, right? So I've found my index. How do I swap variables? Remember that I need to swap a sub I and m. Well, I would create a temporary variable int t is equal to a sub I is equal to a sub m is equal to that temporary variable. So 3 lines of code. This is pseudocode. It allows me to skip those kind of minute, unimportant details and just use plain old English. Swap a sub I and a sub min index. There. Now, this is not a function where I return something, so I will simply output A. Right? Again, driving home the point that this is not actual code. This is pseudocode. Right? Now, we've got the idea here. You should be able to take this and translate it to C. If you eventually learn another programming language like Java or something like that next semester, you should be able to take this and translate it to Java. You should be able to take this idea and translate it to any programming language that you're already familiar with. Right? That's why we like to describe algorithms as pseudocode, because algorithms predate computers by about several thousand years. Right? The sieve of Eratosthenes or Euclid's GCD algorithm. These are the things that are thousands of years old. These are algorithms. Just because we invented computers in the last 100 years or so, doesn't mean that algorithms didn't exist before that. Algorithms exist independent of computers, independent of programming languages. And we need a way to describe them. The best way to describe them is through pseudocode like this. Step 1, step 2, step 3. Simply doing a recipe And baking a cake is an algorithm, right? You've got a list of instructions that you have to follow, right? One after the other. So let's take that idea. Hopefully you've committed it to your memory or you took notes on it. And let's go ahead and redevelop it over here as actual C code, all right? So I'm going to call it's going to be a void function here. Let me go ahead and increase the size. Get rid of that for a second. Get rid of that totally. And I'll call it selection sort. Right? And by the way, again, why do we call it selection sort? You're going through, you're selecting the minimum, and you're putting it at the front of the array. You're going through again, you're selecting the next minimum, and you're putting it at the front of the array. You're selecting things, right? There's no deeper secret than that, right? It is what it says on the box, right? So I'm going to go ahead and pass in an array. Normally, when I've been passing in arrays, I've done const int star arr, int n for the size. Is that a good idea in this case? No, because I'm going to be making changes to it, right? You give me an array, and I'm going. Oh, it's unsorted like this one right here. I'm going to be changing your array so that it's nice and ordered for you, right? If you wanted to, you could have deep copy selection sort, where I copy your array to a new array, and I'll sort that array, and I'll give you that sorted copy, right? That's a different design idea, and it's perfectly valid to do that, right? But in this case, no, I'm actually going to modify your array, right? And by not having const there, that's an explicit, as explicit as it can be, advertisement that I'm going to be changing your stuff, right? All right. So I'm just going to transcribe what we have over here. For int I equals, here we'll start it out at 0 because we're not using one indexing anymore, mathematics. We are using the C programming language that uses 0 indexing. I is less than n minus 1, right? Because over here it was up to n minus 1, but if we're shifting everything down by 1, it's going to be n minus 2. The strictly less than gets us that. I++. By the way, there would be no problem with you doing it all the way up there. It's just that the last element, right, you'd say, all right, well, find the minimum among this guy. All right, I found it. Swap it with itself, right? And it's kind of pointless to do that. So I'm going to skip that. Right? Now, establish your min index, int min index. And that's what I'll actually call it here. And you can set it initially equal to I, like I did right here. For int j is equal to I plus 1. I'll go ahead and plus 1 there. I didn't on the pseudocode, but you're able to skip one ahead if you really want to. I is less than n. I will go all the way to the end on this one. I plus plus. Now, if the thing at arrays of min index is less, than what j is less than what I've found so far, arrays of min index, then I'm not going to swap it right away. Instead, I'm just going to keep track of that minimum index, min index. I'll update that to j. If you really wanted to, you could take this entire 1, 2, 3, 4, 5, 6, 7 lines of code here and put it into another function called getMin or getIndex of min if you wanted to. And then you would reduce, we call that reducing your cognitive load, right? You have to look at, okay, a for loop and another for loop. Maybe I can take this chunk and put it into a function and just call that function that I know that works, and I don't have to worry about the details of that anymore, right? All right, I found, by the end of this for loop, this inner for loop here, I've found the minimum index, and so I will swap a sub I and a sub min index, right? And to do that, I will need, there is a trick. They used to, I've heard of several interviews that have asked this, not recently, but there is a trick that you swap two variables without the use of a temporary variable, right? Think about it for a while. It's just basic algebra. Think about it for a while and see if you can do that. Otherwise, just then look up the answer on the internet. You've got x and y, integers. Try swapping them without the use of a temporary variable. It leads to unreadable code, but you can do it. It's a little trick. Right? I'm not going to do that because I don't want unreadable code. Readable code is far more important than your little tricks. Right? So a sub I. Right? And a sub I is array. There we go. And array sub I then will take on the value array sub min index. And array sub min index will take on that temporary value. Right? I'm swapping inside the for loop because the for loop runs, the ith iteration, I minus 1 elements have been sorted, so you just need to take care of the remaining ones, n minus I of them. Right? All right, that's selection sort. Let's go ahead and see if it actually works. I've got an array here. It's unsorted. Right? Array and n. And then I print everything out. So let's make sure that it actually works. Darn it. Did I screw up somewhere? Thank you. Where? My second for loop. J. Oh, duh. J. I need to stop talking when I'm coding, but I can't do that. All right. Can't do two things at once. There we go. 0, 1, 2, 3, 4, 4, 5, 5, 9. Right? That's the same array that we were playing around with on Monday. Right? And it works. Great. We've solved that problem forever. Right? All we need to do is selection sort now. Right? Well, the first problem is you never do this. You never actually write your own sorting algorithms. You're wasting your time. You are ignoring the huge amount of resources and man hours that have gone into writing the standard library functions, debugging and testing the standard library functions. The standard library functions work. There is an excellent sorting function built into the C standard library that we'll look at later next week. So you never actually do this in practice. But second, that is a terrible, terrible algorithm. Right? To show you why it's terrible, what I'm going to do is I'm going to go back to the .cam here. And let's look at it from the perspective of pseudocode here. And let's ask the same question that we did with respect to the other algorithm, the other algorithms that we did, which were linear search and binary search. We asked the question of how much work do they do. We asked the question of, and then what did we mean by work? And we looked at the algorithm long and hard and said, okay, well, probably that comparison there. So the same idea here is I'm going to focus on this comparison right here. Right? There are lots of other things that you could do. Well, I want to analyze this algorithm with respect to the number of swaps that it makes. Or I want to analyze this algorithm with respect to the number of additions that it makes. Okay, fine. There are additions here implicitly. But generally, those things are necessary for the control structure of the algorithm. There are things that are far more common or far more expensive elsewhere. This is definitely the most common, right? Because it's inside these two for loops right here. Okay. Now, what I could do is I could take that implementation and then have a counter, like I did with the recursive solutions that we looked at last week. I kept a counter for how many times this function was called. And I showed you that, wow, it's huge, right? And then when we cut it down with memoization, we only called it 50 times, right? I could do an empirical analysis if you really wanted to on that code over there. But what I want to do is I want to look at it from an abstract perspective. That empirical analysis would only be relevant to this computer on that data set. Actually, not even this computer because it's being run on the cloud at the REPL site. I have no idea what their computers are running. But we don't want to look at it from that perspective because I can take those computers that it's running on, swap them out with better computers tomorrow that are twice as fast, and it would operate twice as fast. It would be doing the same number of operations, though. So I want to get a hold on the number of operations with respect to the size of the input, n. Right? I'm going to be developing a function to do that. A mathematical function, not a code function. So my question here is, we'll use more fine-tipped here, how many comparisons are made by selection sort on an array or collection of size n. Right? Now, it might help to number these lines so that we can refer to them. 1, 2, 3, 4, 5, 6, 7. Right? And if you focus on, we call this the elementary operation. If you focus on only one elementary operation, then that means that you can start ignoring other things. The question becomes, how many times does it get executed on line 4? Right? So in parallel over here, what I'll do is, I'll do it over here. Right? On line 4, how many times is that executed? In other words, if I ignore everything else, how many comparisons am I doing on that one line? Just one. Not a trick question, just one. Right. Now I'm going to expand my question out here to how many times is line 4 executed? Right. So to answer that question, I need to expand out my consideration here. So how many times is line 4 executed with respect to line 3, the for loop there? It goes from I up to n, right? So n minus I. I think it's minus 1 technically, right? There we go. Is that right? Yeah, that's right. It's because it runs from I plus 1, I plus 2, I plus 3, right? It runs from I plus 1, I plus 3, I plus 4, plus 4, dot, 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 all the way up to n. How many things are there here? 1, 2, 3, 4. How many things are here? Well, a nice way of thinking about it is 1, 2, 3. How many things are here? If I go 1, 2, 3, up to I minus 1, there are I minus 1 things here. Right? I'm not summing the numbers, not 1 plus 2 plus 3. Right? I'm asking how many things are there to count here? Well, how many things are there to count here? 1, 2, 3, all the way up to n. So n. So therefore, how many things are right here? The total minus what you skipped, I minus 1. Right? And that's where I got this. Okay? These are just tricks. This is just algebra at this point. Right? So now, expand this question out again. How many times is line 3 executed? So if I expand line 3 out to this, well, it's located inside of another for loop. That for loop executes multiple times. How many times does that for loop execute? n minus 1. Right? So if I bring all these three things together, how do I bring all these three things together? For each loop here, you're doing a certain number of calculations here. For each time, do I add them together? No. Remember when we looked at matrices? If we had a 10 by 10 matrix, each row had 10 elements. Yeah.
Sorry, I think I left my phone.
All right, you're good. Oh, there you go. All right. All right. So we're going to have to multiply these together just like we did when we looked at matrices. So if I all right, I really don't want to do that math. I can do that math, but I don't want to do that right now. So how could I make an estimate? Look at this right here. Can you give me we want to look at this in the worst case scenario. Can you give me something that's larger but that's simpler to work with? N, right? N is bigger than n minus 1, right? Because n is always positive because n is capturing the notion of how big your array is. And can you have a negatively sized array? No, that'll never happen. Right? So if this were negative, then you could say, well, you can't make that determination. Right? Not enough information. All right, look at this figure now. So I need to multiply by this figure. But I don't want to have to worry about the details. What's the largest term here? And minus 1? No, we just saw that we can kind of ignore that. All right? And by the way, it's also plus 1, so maybe you can't ignore it if you're making it bigger, but I'm going to ignore it anyway. N minus I how can I make that bigger without, I mean, what's I going to run from? I up to n minus 1. So this is going to be at most 1, or at least 1, but at most what? N minus 1, right? That's another overestimate. But again, I'll do the same trick as I did down here and ignore that lower order term there. So n times n, and then this one is just 1. So multiply n times 1. This simplifies to, and I won't say equal, I'll say this is all about n squared. Right? Tell me about this function right here. How would you characterize that function? Is that a linear function? Is that a logarithm? No. What is this? It's a quadratic. Right? Tell me about quadratics. Are they good? N squared. So let's think about this in terms of computational resources. Number of comparisons kind of trucks with the number of CPU cycles on an actual machine, right? That if I wanted, let's look at it from a couple of perspectives. What if I wanted to sort an array of 1 trillion integers? And again, 1 trillion is not that big. That is 4 trillion bytes. That's less than 4 terabytes. Now, it's big from a consumer point of view, but you can get 4 terabyte hard drives at Best Buy, right? That's not that big of a deal. If you're doing real computation over in HCC, the Holland Computing Center, then you're dealing with big numbers like this all the time, or big collections of stuff like this all the time. 1 trillion integers, that's 10 to the 12, right? That's my n. So if I square that, then that's going to be 10 to the 12 squared, which is equal to what? Say what? 10 to the 24. Anybody know what they call those? What's a trillion? I don't know either, right? So how long would that take? Right? Now, that's an engineering question. That's a how fast is the computer you're running it on question. Right? So keep that in mind, and we'll answer. We'll get a better estimate of Wolfram Alpha here in a second. Okay. Let's look at it from another perspective, though. What if I double? What if you increase the size of an array 10-fold? That's an order of magnitude, right? So you go from 1,000 to 10,000, or you go from 1,000,000 to 10 million, or something like that. In other words, you go from n to 10n. Before, it was costing you n squared computation things, right? Computation dollars, if you want to look at it that way. Right? What's it costing you now? Before, it was costing you 10n dollars, whatever you want. Now it's costing you that squared. What is that equal to? 100 n squared. In other words, it's 100 times slower just by going up by a factor of 10. Right? Look at it any other way. If you double the input size, 2 instead of 10 here, then it's 4 times as slow. If it's 100 times as big, it'll be 10,000 times as slow. So the higher order magnitude of n that you get, the larger and larger n you get, the more apparent that disparity becomes. Right? So now let's go ahead and ask Wolfram Alpha. Let's get an estimate here on how long this would actually run. I'll open up Wolfram Alpha, and we said that it would take 10 to the 24 operations. We call those flops, floating point operations per second. Right? So I don't know. Does anybody want to flex? Does anybody have a? Let's see, a 2080 Ti? No. All right. Does anybody have a 1080 Ti? Oh, okay. All right. Secondary market or? How much was it? Now, how much are they going for now? 6, 7?
They're around 550.
550? Okay.
Or 750.
All right. Do you know how many flops it has, or how many teraflops it has, or gigaflops? All right. Well, we'll just say I don't know flops of a 1080 Ti. It's not very comparable to an actual processor because you're talking about what do they call them? Not nodes, but it has like it doesn't have full processors. It just has GPUs, right? That's what it probably has. So I'm just getting comparisons. Flops of a 1080 Ti. You don't upgrade ultimate. Okay, we're just going to get commercial stuff there. So let's just say that there's 1 teraflop, 1 or 10 to the 12. That's huge. You're probably not getting that out of your 1080 Ti. You're not even going to get that out of your 2080 Ti, right? That's 1 teraflop. That's 1 trillion floating point operations per second. Right? I don't know. Maybe somebody can look that up and tell me what it is. Right? That's per second. There are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. So how many days is it going to take for us to do this? That's 1.15 10 to the 7, so we're in the realm of millions. That's 10 million days. All right, fine. Well, then how many years? 365.25 days in a year. All right, that's much more manageable. That's only 32,000 years. Right? Is that right? That's my estimate, right? So, is that a good algorithm? No. I mean, you can defrag, or you don't defrag hard drives anymore, but you can certainly write a hard drive in a matter of a few hours if you're wiping it out, or an SSD maybe a few minutes or something like that. But you could certainly take one SSD and sort everything and put it onto some other SSD. That's within the realm of possibility. This is not in the realm of possibility. So some other algorithm must be at play here. Right? That algorithm, I won't give you the name yet, but I will give you the idea. Let's see. Let's go back to the doccam here. Right. And what were the original numbers that we did? That's all right. I'll make up new numbers. Right. So here's a better solution, a quicker solution. 8, 3, 4, 9, 10, 1, and 2. And let's see, 12. There we go. So here's the idea. What I'm going to do is I'm going to take this first number, and I'm going to treat this as what's called a pivot. So what is a pivot? Basketball season started. Let's see, they lost to UC Riverside, right? What's the next game? Volleyball's tonight, I guess, right? Right? So they lost to Southern Utah? Oh, okay. All right, enough talk about that. What is a pivot in basketball? You take 1, 2 steps, that's your pivot foot. Can you pick that up with the ball? If you do, it's traveling, right? Never called, but it's traveling. So what can you do with it, though? You can pivot around it. What we're going to do is we're going to take the rest of this material, rest of these numbers, and we're going to pivot around this. If it's less, we're going to go through this list of numbers. If it's less, we're going to put it over here, 3, 4. If it's greater, 9, we're going to put it over here, 9, 10. 1 is less, 2 is less, 12 is greater. After we're done, we've separated this into a left partition and a right partition. Where does 8 belong? Right in the middle, the place that you pivoted around it. Right? Now, if I were to actually sort this, 8 is where it needs to be. What do I do with this, and what do I do with this? I sort it, and I sort this. I repeat that process. Let's sort this. All right, so cover everything else up here. I'll choose a new pivot element, 3. And I will go through the rest of this stuff. 4 is greater, 1 is less, 2 is less, 3 goes right where it needs to be. Right? And now I've separated this out into two lists. What can you tell me about that list right there, that array? It's sorted by definition. I would continue on this, and I would find that this is a pivot, and 2, okay, well, that's where it needs to be. 1 goes there. And now I've got an empty list, which by definition is sorted. I've got a single element list, which by definition is sorted. This half is now sorted. 8 never moved. Repeat that process over here. 12 is my pivot element. So 10 is less, 9 is less, 12 ends up being there and fixed. So I've got an array of size 2. I've got an empty array, so I don't need to do anything here. This is my new pivot element, and so 9, it's less, 10, I put it right there, and everything carries through. It's all sorted now. Right? Describe that kind of approach, where I put it into 2 lists, and then I sort each one. I'm dividing it, and then conquering it. Right? So you could develop a recursive algorithm to do something like this, right? Where you've got this partitioning, that's the non-recursive work, and then you make one recursive call to the left part of it, one recursive call to the right part of it. And then you keep going until what's your base case? When you have nothing left, or when you have a list of size 1, in which case, by definition, it's sorted. So your base case, your recursion, your non-recursive work to get to set up the recursion. Right? This thing is called quicksort. Okay. I'm not gonna code it because it was a good exercise to go through selection sort. If you want to, there's plenty of code samples on the internet and in the book on how you would do quicksort with a bunch of different variations on what's the best pivot choice, selecting a random pivot choice. The ideal pivot choice is, of course, the median. But how do you find a median? Here are 100 elements. How do you find the median? Sort it and then just choose the middle one, right? So putting the cart before the horse, chicken and the egg, whatever, you're not going to do it in a practical sense. Right? All right. I will, however, tell you, and it's beyond the scope of this course, we use something called the Master Theorem to set up a recurrence and then find a big O analysis of it. But we haven't talked about big O, so I'm not going to do that. Instead, I'm going to tell you that quicksort makes roughly about n log n comparisons. Right? Now, that's in the best case. In the average case, in the worst case, it devolves into selection sort, actually, in which case you'd have n squared behavior, but we're not going to worry about those details. What I want to do is I want to look at this from the same perspective that we looked at everything, the order n squared, the n squared algorithm, the selection sort. Right? Now, if I wanted to sort a 1 trillion 10 to the 12 integers, then if I plug that in up here, what do I get now? 10 to the 12, so it's 1 trillion, times log of 10 to the 12. All right? Now, log identity is what happens to this 12. Comes out front. So you are paying for, you're paying for a lot here, but you're certainly not paying as much as you were with selection sort. Times log, and by the way, what was my base here again? 2. We're self-respecting computer scientists. We only use base 2. Right? Log base 10. Right? We'll go back to Wolfram Alpha and ask the same question here in a moment. But before we do that, suppose we look at it from the same perspective as before, that if I increase it by 10-fold, if I have an array of size n, it'll take a certain amount of time. If I go from 1,000 up to 10,000, or from 1 million up to 10 million, right, 10-fold increase in the size of the input, then n log n, what happens here? It goes 10n log, or 10n log 10n. Right? No squared factor here, but we need to figure this out a little bit at least. So 10n, what can I do with this log? 10n. Log of 10. It's multiplication in here, so if I separate them out, log of n. Oops, there we go. Which is equal to, that's about 3 point something something something. So what I'm going to do is I'm going to take the largest order term here, same trick that I did before when I analyzed the selection sort. I ignored the lower order terms, plus 10n log of base 2 of 10, right? Forget about that. All right? So tell me about this now. Oops, sorry. How much bigger is this than before? 10 times as big. As big. Right? Sounds familiar, right? If we ignore the lower order term and cheat a little bit, sounds really familiar. If I have a linear function and it has a certain value at n, and I go up to 10n, what's its value now? 10 times whatever it was before. Just like this, 10 times bigger, 10 times as big, 10 times as slow, right? So this is almost linear. And we have a name for that. Desdemona and Quasimodo. Quasi, almost. Quasimodo is almost man. Quasi-linear is almost linear. Well, it's linear if you put your finger over that, right? Logarithm terms, those are super slow growing, so we might as well consider it as a linear thing, right? But we call them quasi-linear instead. It only takes 10 times as much computation power if you're using that fast quicksort algorithm. There we go. All right. So let's ask Wolfram Alpha here the same question. The only difference here is that we've got 10 to the 12 times log base 2 of 10 to the 12. And make sure that all of that is in the numerator. And we ask the same question again of how many years does it take to sort that thing? In this case, however, it's several orders of magnitude lower. That's a -6 there, so we're asking the wrong question here. It's not going to take years anymore. Might not even take days. Does it take hours? Well, it's a lot of stuff, so nope, it doesn't even take hours anymore. Does it take minutes on that 2080 GPU or whatever you're getting 1 teraflop out of, right? So how many minutes does it take? 2/3, right? So it's taking you about how many, right? That's per second. So is that even 1 second? That many flops per second, yeah, that's going to be 39 seconds. I was right, about 40 seconds. Right? The previous one was a minute, so 2/3 of a minute. Well, 2/3 of a minute is 40 seconds. So it's noticeable, right? If you ran this program, you would notice it running. You would not see it stop until 40 seconds later. But at least it's not 32,000 years in the future. There is a huge disparity between these two performances. Right? And to demonstrate that further, I've set up an example here. Well, this is what we'll end on today. And it also gives me the opportunity to show you another tool, gprof. Where is it? Oh, this is the class account. All right. So oftentimes you might have, in fact, in this class, some people have submitted stuff that has been a runaway process, that they accidentally had an infinite loop, and it just kept running forever. How do you distinguish whether or not something is just really slow and it's going to take a long time to actually execute versus something that has an infinite input? It just keeps going and going and go, or infinite loop, and it just keeps going and going and going. Some people are, especially with assignment 4, be careful. Don't submit it with an infinite loop or even a large loop, because some people have been writing files and they've written like 30 gigs of data, and then of course our quota goes out and it locks everybody else out until we go back in and delete those files. So please don't do that. How do you do this? This is called generally performance testing, or because everybody likes to shorten things up, it's called perf testing, or perfing, right? Where you are checking the performance of a certain algorithm or a certain piece of code, right? What I've done here is I've set up several examples. So you're actually going to be working on this data set for Hack 14 and for your last assignment. This data set, I don't even want to open it. No, it's 16 megs. I'll just a little bit of it, data. There we go. So there are 100,000 records here. The actual data that you'll be working with, I think, has 160 million records or something like that. And then we select a small subset of it. These are transaction IDs. So this is fake data. This is artificially generated data. But they're transaction data. Some of these things are payments to a system. Some of these things are deposits. That's the amount. That's the account. The second thing is the account. This is the amount before, the amount before your balance beforehand, and then this is your balance after, and then this is the destination account if it's a payment or a deposit. Right? So a whole bunch of transaction data here. I want to know, is this data correct? So there are lots of questions that you can ask of, is it wrong? Is there fraud in there, which is what you're going to do on your final assignment? Is there something weird in there? I just want to answer a simple question. Do I have a duplicate record? In other words, this record, this transaction right here, should be a unique ID. Is it a unique ID? In other words, is there some other record way down here with the exact same thing? Sounds kind of familiar, right? Hopefully you're doing homework 4 right now. What are you doing in homework 4? You're finding unique lines, right? So same basic idea. And by the way, we're not expecting you to do searching and sorting. We keep that data intentionally small. But what I've got here is a couple of examples of how you can go about solving this. Let me go ahead and go with duplicate checker, quadratic. Yeah, quadratic. There we go. So this is very simple. It loads up the database, whatever. It has 2 for loops, just like selection sort. Right? So it runs through, and for each one, for the ith one, it runs through all of the others. Right? J is running from I plus 1 up to n. And then it does this comparison of, do the transaction IDs match? Right? Does this transaction ID equal this transaction ID? If so, that means that we found a duplicate. We increment a counter to see how many duplicates we actually found. So if something is actually duplicated, here's A here again, then we'll double count it. We counted it here, and then we counted it here. But fortunately, I've made sure that there's no duplicate data in here. So we should get an answer of 0 every single time. That's a naive way of doing it. Make everything, let's see, don't worry about that. Find, dupes, slow, brute force. Let's go ahead and go with 1,000 of them, and then the data file. That's how I've set it up here. 1,000 of them. Pretty fast, right? The way that worked is it checked the first 1,000. Right? Let's check the first 10,000. Right? 1, 2. Okay, that was a little bit noticeable. Right? Let's check all 100,000. 1, 2, 3, 4, 5, 6, 7, 8. While somebody else count in their head while we're going here, don't worry about counting. I went from 10,000 up to 100,000, and I was kind of using a selection sort kind of thing where I've got 2 for loops in there, probably meaning that it's going to be quadratic, right? Just like I labeled the file, right? It's quadratic, slow, brute force. So 10 times as big, the math that we just did tells me that it's going to be 100 times as slow. If 10,000 took 2 seconds, then 100 times slower is going to take 200 seconds, which is going to be around what? 2 minutes, 50 seconds, something like that, 3 minutes, whatever. Right? I'm not going to wait for that. I'm going to kill this. Right? What I did instead is I have an alternative here. What is it called? Quasi-linear. Emacs. Quasi-linear. This is what we're going to be looking at on Monday. I'm calling a function called qsort to sort it. What do you think qsort stands for? Quick sort, exactly. I'm sorting it. How can I exploit the fact that it's sorted? I could use binary search, but if it's all sorted by the transaction ID, where are the duplicates going to be? Right next to each other. All I have to do is check I and I plus 1. If those match, then I found a duplicate. Right? So find dupes fast, same data file, and 10,000. Remember that it took 2 seconds before. Immediate. It wasn't even noticeable then. 100,000 before we guesstimated that it was 3 minutes. Immediate. Right? You see the stark contrast here with even a small number. I did 1 trillion over here to be dramatic and to give you 32,000 years. But the same difference here of like immediate 10 milliseconds or whatever it was versus 3 minutes, you can start seeing those huge differences. In other words, algorithms matter. Efficiency matters. We can find out just how bad this is by running what's called a performance tester, a profiler, or a perf tester. I have to remind myself how to do this. It's in the README file. gprof, okay. Gprof, let's see, what was it called? Find dupes, slow, brute force. Right? So let me go ahead and clear this out and run that again. So what I did is I set up a performance tester. I set it up beforehand that when it runs, it also actually produces this report file. And this is a utility that I need to use to actually read the report file. 100% of my CPU time here, more than 100% it looks like, rounding errors maybe, I don't know, made 100,000 calls, or 999,999 calls, taking a total time of 300 milliseconds, or nanoseconds per call, 300 nanoseconds per call, and a total time of 0.03 seconds. This is only on 10,000. This wasn't the 3-minute run. And everything was done in this compare transaction by ID. Well, of course, because it was, I called it, 100,000 times. So the vast majority of my time is going to be spent there. Right? And you can get other information out of it. This is a call graph. Well, who was making all those expensive calls? The main method, the main function was calling it. Load database was calling it. And here's other things like a deep copy string. Well, there were 300,000 calls to that, but it didn't take any time at all. The real problem up here is these 2 calls. Everything else was completely unmeasurable. It took essentially 0 CPU time. By running a profiler, it's telling me who's responsible for this terrible performance. Perf testing. And you can have a call graph made like this. You can even use heat maps. Heat map code. Right? Heat maps, of course, tell you the hot areas. Images. Nope. I'm going to. So you're going to get heat maps of the United States, of hotbeds of whatever you're talking about. Heat map code. I don't know. Profiling. Performance testing. There we go. So you can get heat maps that look something like this. Well, the code over here, this library, it's pretty fast, right? We don't need to worry about improving the performance over there. But this stuff over here, that looks hot. We need to take a closer look at that code and see what's going on. Check it out, check it out. Oh, this guy wrote his own version of selection sort, which I know to be a terrible algorithm because I paid attention to my CSE curriculum. All right, so I'm going to take his code, throw it away, replace it with a quick sort, run the perf testing again, and now it's immediate. Right? So performance testing can be a huge beneficial tool. Not that you'll use it directly in this course, but you can see already the stark difference. If I run the performance testing for find dupes, what was it, fast? Fast? Right? There we go. Go back up here. You can see that I'm making similar number of calls here, but the time that it takes 100% here. The time was similar because they were both done with 10,000 or something like that. But you can run the performance testing, the perf testing before your improvements, run it afterwards, run a profiler afterwards, and see, okay, I improved that. That hot area right there is now green, and I don't need to worry about it anymore. Now let's focus our efforts over here on this heat map area, this hot area, and try to increase its performance. And if you have a very slow running application or something like that, you need to look for those bottlenecks. You need to look for what is actually slow in order to fix it. It's kind of like debugging, but there's no bug, right? Your code works. It just takes a really long time. But performance testing is another tool in your arsenal to find out what's taking so much time, and can I make it take less time? Right? All right, when we come back on Monday, we'll talk about how to do this actual stuff in practice, right? So that we don't have to write our own stuff every single time.